This is AP Calculus 5-7, using the second derivative test to find relative extrema. This is just another way of finding relative maximums and minimums, or local maximums and minimums. The first derivative test will find your extrema, and the second derivative test will find the extrema. It's very important to understand that when we tested the second derivative for concavity, that was just a test for concavity. That was not called the second derivative test. The second derivative test will find the same thing that the first derivative test will find. It will find where your relative extrema are. In the second derivative, we learned that f prime, when you find f prime, you're looking at whether a function is increasing or decreasing. If the slope is positive, the function is increasing. If the slope is negative, it's decreasing. If the slope is 0, it has a horizontal tangent line at that point. And where you have a change from increasing to decreasing, you have your relative maximums. And where you have a change from decreasing to increasing, you have a relative minimum. We can use the second derivative, f double prime, to also find our maximums and minimums. If you think about it, I just have a real simple graph here. And if you think about this graph, my relative maximum is going to be here that's at -1. And my relative minimum is here at 2. And if you think about that, everything that we've talked about in this section so far holds true. F prime is positive here. F prime is negative here. Where it changes from positive to negative, we have a maximum. F prime is negative in this section and positive in this section. Where we have a change from negative to positive, we have a minimum. Now, how can we use this information to come up with our maximums and minimums using the second derivative? Well, we learned that the second derivative, or f double prime, is a way to figure out concavity of your graph. So if you think about it, if f double prime at -1 is concave down, and we know that -1 is one of our critical values, then doesn't that tell us automatically that at x equals -1, we have the relative maximum? Because any critical value that we find using the first derivative is going to give us the values where we could possibly have a maximum and minimum. If we have a critical value where f double prime is negative, then that means it's a critical value where it's concave down. And if it's concave down, then that critical number is going to be a relative maximum. You have maximums when the function is concave down at your critical values. If you have a critical value that is concave up, then that tells us that when you have a concave up critical value, then it is a minimum. So it's opposite of what you would think. If it's concave down at a critical value, you have a maximum. If it's concave up at a critical value, you have a minimum. And we can find these using charts. We don't even have to have a graph. We can make a chart to find these critical values using the second derivative test. So we're going to do an example using the second derivative test. The second derivative test has this method. First, you're going to find the critical numbers. You're going to find the ordered pairs at those critical numbers. You're going to find f double prime. You're going to plug the critical values into f double prime. And then you're going to determine if f double prime is positive or negative. If f double prime is positive at your critical number, then you have a minimum. If f double prime is negative at the critical number or critical value, you have a maximum. So go ahead and pause the video, get that down in your notes, and then we'll do an example. So in order to solve a problem or find your relative extrema using the second derivative test, the first thing we have to do is find the critical values or critical numbers. Now, remember back when we found critical values, what we do is we find the first derivative and we set the first derivative equal to 0 and we find where the first derivative is undefined. So let's do that first. F double prime is equal to -15x to the 4th plus 15x squared. I'm going to set that equal to 0 to find my critical values. I can bring out a -15x squared, and that leaves me with x squared minus 1. So when I set each of these factors equal to 0, I get x equals 0, and this one gives me x equals plus and minus 1. So we have three critical values here, at 0 and positive and negative 1. The next thing I'm going to do is I'm going to find the ordered pairs associated with these x values. So I'm going to set up a chart, and I'm going to put these ordered pairs in order from left to right, that they would come up, or that they would show up on the coordinate system. So my lowest x value here is negative 1. So that's going to be the first ordered pair. The second ordered pair, the one that comes next, is the one that starts with 0, and the third is the one that starts with 1. And so then I'm going to, in order to find these ordered pairs, I plug those x values into the original function. So if I plug negative 1 in, I end up with negative 2. When I plug 0 in, I get 0. And when I plug 1 in, I end up with positive 2. So I found the critical values, and then I found the ordered pairs for those critical values. I'm going to use these ordered pairs, and I'm just going to set up a little chart. The next thing it tells me to do is to find f double prime. So what I'm going to do is I'm going to make a chart out of this. And I'm going to just put an f double prime here, and I'm going to figure out whether this ordered pair for x equals negative 1, whether f double prime is positive or negative. Now understand, these are not intervals. These are ordered pairs. They are exact ordered pairs, not intervals. So if I plug negative 1 into the second derivative, and all I'm interested in is whether it's positive or negative. So if I plug negative 1 into f double prime, well, I don't have f double prime. I only have f prime. So I'm going to clear a little space and find f double prime. If I find f double prime, I'm just going to take the derivative again. That would be a negative 60 x cubed plus 30x. And if I plug negative 1 into this function, I would have a positive number. If I plug 0 in, I'm going to get 0. If I plug 1 in, I have a negative number. Okay, now I need to use this chart to determine where my relative maximums and minimums are. Now, we've plugged into f double prime. Now we need to analyze what we got. If f double prime is positive or greater than 0, this one is positive, then it's concave up. So that means at the point negative 1, negative 2, the graph is concave up. So if it's concave up, it looks like that, making the point negative 1, negative 2 a minimum. So we have a minimum value at the point negative 1, negative 2. If f double prime is negative or less than 0, we have something that is concave down, and if it's concave down, we have a maximum value. So we have a relative maximum at the point 1, 2. Now, we did not say anything about what happens if f double prime is equal to 0. If f double prime is equal to 0, the test fails. And if the test fails, then we have to revert back to the first derivative test. So if you think about what we did with the first derivative test, we would test the values, since 0 is a critical value. We would test the intervals leading up to and on the other side of that critical value of 0. So if you think about that, our critical values, remember, were plus and minus 1 and 0. So leading up to your 0 interval, that would be the interval from negative 1 to 0, and then 0 to 1. So we need to test, using the first derivative test, those two intervals to see what actually is happening at 0. And if we do that, we're going to choose a number in the interval, like negative 1/2 and 1/2. And remember, the first derivative test tells me to plug those into the first derivative. When I plug negative 1/2 into the first derivative, I end up with a positive. And you can check these on your calculator. When I plug 1/2 into the first derivative, I'll end up with a positive again. Since there is no sign change here, we don't have a relative maximum or a minimum. We just have a critical value there. And what is probably going to happen if you were to analyze this graph further, I would guess that that's probably a point of inflection, but we'd have to do a little more investigation to figure that out for sure. So we've used the second derivative test to find your relative maximums and minimums. Honestly, the second derivative test is more time consuming, I think, and more confusing than the first derivative test. So if given a choice, I'm always going to use the first derivative test to find my relative maximums and minimums. I think it's a lot less work. But there may be occasions where you don't have a choice and you have to use the second derivative test. That happens when they give you a chart or just some ordered pairs for your function, but they don't give you the entire function. So they might give you a table with some of the ordered pairs instead of giving you the entire function. But if they give you the entire function like this, it's going to be a lot easier to use the first derivative test. The only time I would use the second derivative test is if they give me a table of values and ask me to find the maximums and minimums, and they haven't given me the intervals associated with the entire domain.